Next, we will introduce the Euler's constant and discuss its significance and applications in the context of limits of exponential functions. Consider the following function. As x goes to infinity, we have the following tendencies. For b greater than 1, the output should approach to infinity. However, as x goes to infinity, the base approaches to 1, which makes the output grow slower. So what would it be at infinity? Infinity or 1? Let's take a look at the graph. There appears to be a horizontal asymptote. In other words, we are looking for the limit of this function as x approaches to infinity. With a quick substitution, we see that finding the original limit is the same as finding the limit of this new function as the input approaches to 0 from the right. Superimposing the graph of the new function allows us to see that indeed the two limits are the same. Let's zoom in a little and zoom in a little more, and one more time. We see that both limits are approximately equal to 2.7183. We call the limit of these two functions e, the Euler's constant. And it is approximately equal to 2.71828. But just like pi, it is an irrational number that has no pattern. This limit can be a starting point for deriving many other interesting non-trivial limits. For example, consider the following transformations. Rewrite the statement without the word limit. Raise both sides to the power x. Subtract 1 from both sides. Divide both sides by x. And voila, we have a new limit statement. In summary, we now have two limit statements that involve e, the Euler's constant, that we add to our toolbox of limits. We introduced the Euler's constant and discussed its significance and applications in the context of limits of exponential functions.